All right, good morning, everyone. We are moving on to chapter 11 today, which is about balancing chemical equations. A lot of people enjoy that, so hopefully you're one of those people. If you do not enjoy that, it's like kind of like a logic puzzle. So we're just going to do an intro on it today and talk about some different types of equations, and then it'll get more complicated as the week goes on. Quick reminder, in case you've been forgetting, you really need to be reading the chapter and taking notes on it for yourself to further enforce what's happening. I don't necessarily go over every single thing in the chapter. Partially it's because we're online, but partially it's also because, I expect you to do some of that yourself. So make sure that is something that you are doing. All right, so let's get started with chapter 11.1. All right. Okay, so let's start by just describing chemical reactions with words. Okay, in a chemical reaction, the chemical formulas of the chemicals involved are changed. But we're just going to start by talking about the chemicals as words. So the general format of a chemical equation is reactants, okay, on the left side and products on the right side. Now, I know that you are used to writing an arrow sign going from left to right, which is fine. However, since this is a higher level class, I want you guys to start using a double arrow. Okay, typing it out, I did it like this. However, that's not how you would write it if you are writing it out by hand. If you're writing it out by hand, you would write something like this. Okay? It almost looks like an Amtrak sign. All right. So, it's like arrow going to the right, the top half of that, and the arrow going to the left, the bottom half of that. Okay? The reason why we use the double arrow is because every chemical reaction can go forwards or backwards. All right? So, to be more accurate, we're denoting the chemical change with the double arrow that tells us that our reaction can go forward or backwards. Now, most reactions only generally go in one direction, which is why you're used to seeing the arrow going from left to right. However, all reactions can go forwards or backwards. It may be very, very difficult to make it go backwards, but it could theoretically go backwards. So we're going to start using the double arrow to indicate that. Okay, so try to get used to that. Try to get in the practice of doing that instead of writing the one arrow, writing the two arrows. Okay, so like I said, reactants are on the left, products are on the right. Although if you think about the double arrow, that's a little bit of a misnomer because, like if you go in the other direction, it feels like the products are going to be on the other side. So just remember that by convention, reactants are the left side, products are the right side, even if it's a double arrow equation. So we're going to write iron reacts with oxygen to produce iron 3 oxide, which is rust. Okay, and we're going to write that chemical reaction in words. So that's what we're going to start with. And all I'm saying when I'm saying write the chemical reaction in words, which is not something you're going to have to do, but I just want you to slowly get used to how the chemical reactions work, or get reused to it, since this is probably a review. Okay, so you're just going to say that iron, okay, plus oxygen yields iron 3 oxide. So we're just going to write out the chemical formulas. We're going to write out the chemical names. So iron plus oxygen yields iron 3 oxide. So we're describing in words what the reaction is. All right. So another one. Hydrogen peroxide decomposes into water and oxygen gas. Okay. Hydrogen peroxide decomposes into water and oxygen gas. So I'm just going to say hydrogen peroxide and then double arrow, water and oxygen. Okay, so I'm just writing out in words, or I'm writing out the chemical equation in words. Okay, so that's where you start. Okay, so another thing that I forgot to note is that you're going to read the arrow or the double arrow as yields. So if I go back to this, I'm going to say hydrogen peroxide yields water, and oxygen. Okay, so read that double arrow as yields. So let's go back to this equation. Iron reacts with oxygen to produce iron 3 oxide, which is rust. So I say iron plus oxide yields iron 3 oxide. Hydrogen peroxide decomposes into water and gas. Hydrogen peroxide yields water and oxygen. Okay, the next step we want to do, and really the important thing, is that we are going to write the chemical equation with formulas. So, as a reminder, again, reactants on the left, products on the right. Iron plus oxygen yields iron 3 oxide. Let's start with this one. Okay, so here is your unbalanced equation. So when you're writing chemical equations, there are multiple things that need to happen. Okay, you need to have the chemical formulas, and in general, these little subscripts here, S, G, S, okay, those stand for solid and gas. Okay, so in general, when you're writing a chemical equation, you're also going to write the state of matter that the equation is in. Okay, now iron is just Fe, oxygen is O2. How did I know oxygen is O2? That's just something you need to know and memorize. Iron 3 oxide is something you could have figured out, you know, like we did in chapter 7 or 8. Iron 3 oxide, iron has a +3 charge, so you need 2 Fe's to mix with 3 O's. Okay, so here's our unbalanced equation. Fe solid plus O2 gas yields Fe2O3 solid. So that's how you would read that out loud. Now, hydrogen peroxide yielding water and oxygen, okay, we can write that unbalanced equation out as well. Okay, again, I just know the hydrogen peroxide is H2O2. So this one I would read as H2O2 aqueous yields H2O liquid plus O2 gas. Okay. S equals solid, you know what a solid is. L equals liquid, you know what a liquid is. G equals gas, you know what a gas is. AQ equals aqueous, which you basically know aqueous is anything that's dissolved in water, we consider aqueous. And so if you think about hydrogen peroxide, it's not 100% pure hydrogen peroxide like if you buy it at CVS or whatever. It's some hydrogen peroxide mixed with water, so that's why that's AQ, aqueous. Okay. Any questions about that? All right, you do not have to unmute, but I want you to practice this. So I'm going to read these equations again, and I want you to repeat after me in the comfort of your own home or at school, on mute, please, just so you get used to this. All right, so this equation is going to be Fe solid plus O2 gas yields Fe2O3 solid. Go ahead and repeat that. Okay, and then the second one is going to be H2O2 aqueous yields H2O liquid plus O2 gas. So practice repeating that as well. All right, so I gave you the unbalanced chemical equations, but all the fun is in the actual balancing of chemical equations. So let's take a simple example first. It takes 2 pieces of bread, 1 slice of cheese, and 3 slices of bacon to make a bacon grilled cheese. Okay, so we can write that out in words. 2 bread plus 1 cheese plus 3 bacon yields 1 bacon grilled cheese. Or we can write that out as a formula. 2 Br for bread plus 1 C for cheese plus 3 Ba, not barium, for bacon yields Br2 CBa3. Okay, so notice that, you know, this is covering all the ingredients that are put together. Okay, so chemical equations is just like making sandwiches, except for you're making sandwiches with elements that you can't see with the naked eye. And you're going to have to balance these sandwiches that you're making. Okay, balancing chemical equations is going to use the same concept as my bacon grilled cheese example. So let's take a look at the rusting example. Fe solid plus O2 gas yields Fe2O3. All right, when you break it down, you want to balance an equation, you need the same number of Fe and O atoms on both your product and reactant sides. So I want the same number of Fe on the left as I have on the right, and I want the same number of oxygen on the left as I have on the right. Any questions about what that means? So let's break this down in practice, because it's just problem solving after you know what you're trying to figure out. Okay, so Fe solid plus O2 gas yields Fe2O3 solid. What you're going to do is you're going to count how many of each atom you have on each side. Okay, so right now I have one Fe on the left and two O's on the right. And I have two Fe's, sorry. I have one Fe and two O's on my reactant side on the left here. And then I have two Fe's and three O's on the product side here. Okay, because Fe2 means I have two Fe's, O3 means I have three O's. Okay, what I'm going to want to do is I want to make it so that I have the same number of Fe's and O's on both sides in this red row. So what I suggest that you do first in this problem is notice that I have two O's on this side and three O's on this side. Okay, I need the right side to have an even number of O's. Otherwise, these two numbers will never equal each other because this one's even, this one's odd. And you can't turn an even number into an odd number. Okay, so what I started with is I just put 2 in front of Fe2O3. Okay, and what this tells me is that instead of having one Fe2O3 molecule, now I have two Fe2O3 molecules. Which just means, going back to the sandwiches, it's like I have two bacon sandwiches now, right? So if my bacon sandwich was 2 slices of bread, 1 slice of cheese, and 3 slices of bacon, if I have 2 bacon sandwiches, now I have 4 slices of bread, 2 slices of cheese, and 6 slices of bacon. Okay, so I'm just doubling what I had. All right, so it's going to be the same for Fe2O3 as it is with a bacon sandwich. So now, as I'm trying to balance this equation, the left side, the reactant side, still only has one Fe and 2 O's. But now on my right side, I have 4 Fe's and 6 O's. Let me stop there. Any questions for how I got 4 Fe's and 6 O's here? All right, so can I get a suggestion for, what numbers do I need to, or let's start with Fe. What number do I need to put in front of Fe to balance the two sides? So if I have 4 Fe's on this side, what number do I need to put in front of this Fe to get the same? Yes. So I'm going to need to put a 4 there. Okay. And if I have 6 O's here, what number do I need to put in front of this to get 6 O's total? Well, if each of these is 2 O's, I'm going to need a 3 in front of there to get 6 O's. Okay. So now I can balance the equation. I put a 4 in front of Fe, a 3 in front of O2, and then I still have my 2 in front of Fe2O3. And now if I calculate it out, I have 4 Fe's, I have 3 times 2, 6 O's. And then on this side, I have 2 times 2, 4 Fe's, 2 times 3, 6 O's. Okay, 4 Fe's, 6 O's, 4 Fe's, 6 O's. Okay, my equation is balanced. Now, super important, you cannot change the coefficients. You cannot change the chemical formula. I can't just make Fe into Fe subscript 4, right? That is changing the formula, and you cannot do that when you're balancing chemical equations. You can only add molecules, okay? If I'm making my bacon grilled cheese, I can't change the number of slices of cheese in it, otherwise it's a different sandwich. The only thing I can do is I can make more grilled cheeses if I have ingredients to use up. Okay, so that's how this goes. All right, so let's take the second example. H2O2 yields H2O plus O2. Okay, so H2O yields H2O plus O2. Now, what I want you guys to do first is tell me right now, without balancing anything, okay, write it down. How many hydrogens are on the reactant side? How many oxygens are on the reactant side? How many hydrogens on the product side? How many oxygens are on the product side? So count the number of atoms on each side of this equation right now. Okay, so let's start. On the reactant side, on the left side, how many hydrogens do I have? And oxygens? Okay, so I have 2 hydrogens, 2 oxygens on the left side. On the right side, I have 2 hydrogens, and then now I have 3 oxygens total, right? So 1 O plus 2 O's here. Okay, so 2 hydrogens, 2 oxygens on the left, 2 hydrogens, 3 oxygens on the right. Now remember, like I said, if you have an odd number of an atom on one side and an even on the other, you're going to have to at least double the odd side to get that to an even number. So I'm going to start by doubling this H2O. I'm going to make this 2H2O so I get an even number here. All right, so if I make this 2H2O, I still have 2 H's and 2 O's on the left side, but now on the right side, I have 4 H's and 4 O's. Okay, so let's count that up together. Okay, so H2 gives me 2 H's. O2 gives me 2 O's. But on this side, I have 2 H2, so that's 2 times 2 gives me 4 H's total. And then 2O plus O2. So 2O, 2 times 1 gives me 2 O's. This O2 gives me another 2 O's, so 2 plus 2 is 4. So now I have 4 H's and 4 O's on both sides. At this point, it should be pretty clear what coefficient, what number do I need to put in front of H2O2 to balance this equation now? That's right. So if I just put a 2 in front of H2O2, that's going to double my numbers of H's and O's, and I'm going to be all set. I have 4 H's, 4 O's on one side, 4 H's, 4 O's on the other side. It's balanced. So let me double check. 2H2, 2 times 2 gives me 4 H's. I'm good. 2O2, 2 times 2 gives me 4 O's. I'm all set. And the right side, we didn't change, so we're all set. So 4 H's, 4 O's on the left, 4 H's, 4 O's on the right, and we are balanced. Okay, so that's how we are balancing equations. These are simple ones, but the concept will remain the same. It is, like I said, problem solving, puzzle solving. You know, you got to take it one step at a time, you know, balance one element at a time. And the best way to get better at it is to practice, which we will do. Now, I want to end the class quickly with some types of chemical equations that exist. Okay. The first one is combination or synthesis. That is element A plus element B yields element AB, or excuse me, molecule AB. So an example, very simple example, 2H2 gas plus O2 gas yields 2H2O. Look at element A plus element B yields element AB mixed together. Okay, so that's combination or synthesis, you know, when you're putting stuff together. The opposite of that is called decomposition. So that's when you start with AB and it yields A plus B. You know, notice these are just two sides of the same coin. So our hydrogen peroxide example was an example of decomposition because, you know, you have hydrogen peroxide and it breaks down into water and oxygen. So that is decomposition. All right, these A's and B's don't have to be elements. They can be chemicals as well. Think about it as, you know, if you're writing it out in words, hydrogen peroxide yields water and oxygen. Okay, it's breaking down into two different parts. Okay, so that's called decomposition. Single replacement is when AB plus C yields AC plus B. So it's called single replacement because, you know, it's like a, you know, like a home wrecker, right? This C comes in, replaces B, B gets kicked to the curb. Okay, so that's single replacement. All right, AB plus C yields AC plus B. So here's an example. 2HCl plus Ca. Ca is the home wrecker. Ca links up with Cl2 or with Cl and becomes CaCl2, and H gets kicked to the curb. It becomes hydrogen on its own. Okay, so that's single replacement when you're replacing one thing. This is a slide that you should save for reference. All right, double replacement is, you know, one of those weird group marriage situations. Okay, AB plus CD, they just switch partners to AD plus CB. So it's, you know, or it's like switching partners on the dance floor or something, if you want to be a little more PG about it. All right, so my example here is 2NaOH plus CaCl2 yields CaOH2. Notice that the OH, you know, remember that's hydroxide, so we treat that as one thing, plus 2NaCl. Okay, so you can see how the partners switched, right? OH went with Ca, Cl went with Na. So these are the four main types of chemical equations. There's one more type called combustion, but that one is much more complicated to balance. So I will save that for another day. But that ends, you know, our introduction to balancing chemical equations and types of chemical equations.